So, welcome to the Target JEE series that is presented to you by Byju's. Now, in this particular video, in this episode, we're going to talk about the chapter Work, Energy and Power. Okay, and it's a nice chapter. It's a very interesting chapter, and I particularly find it interesting to say the least, because the concept of energy is a little weird. It's not very concrete, like forces and laws of motion and so on and so forth. Irrespective, in terms of what we're going to do in this video, we will be giving you an analysis in terms of like the type of questions and the number of questions that generally comes in the JEE papers. After that, we will give you a quick revision of all the most important concepts in this chapter, and then finally we'll jump into the problem solving itself. But before we get started, please don't forget to like and subscribe, especially if you like videos like these. Now, coming to the analysis of this particular chapter, if you look at the type of questions, on average you'll find that there are 2 questions in JEE Main and 2 questions in JEE Advanced every year. On average, this has been the trend for the last 5 years at least. And in terms of the type of questions, most of them have been coming from concepts like finding work, work energy theorem, finding force from potential energy, and conservation of energy. Right? These are, in terms of importance topics, these are pretty important. Overall, coming to the chapter itself, it's not that just because we might think that just because we're getting 2 questions, it's not as important. The truth is, it is very important, because a lot of concepts from this chapter are used in higher chapters or in more complex chapters, like, for example, electrostatics and higher, mechanics and rotational mechanics. A lot of these concepts are used over there. So therefore, this chapter is still very important. Okay, so before we go to the questions, let me quickly go through all the important topics. The first one is probably finding work. Now, work done, as we know, is defined as the dot product of the the force vector and the displacement vector, or F dot S. Now, in the case of variable forces, we find that you have to integrate, right? You have to take a really small amount and you have to integrate and find the integral F dot ds. Okay, this is the definition of work done. All right. Now, then a really important concept that we come across is the work energy theorem, which is generally defined for a point object. It says that the net change in kinetic energy of that object is equal to the work done by all the forces, both conservative and non-conservative. In a sense, you can say that this is actually just another way of writing or saying the law of conservation of energy. When you apply the law of conservation of energy, you get this. So first, coming to the definition of potential energy. Now, that change in potential energy is defined as the negative of the work done by a conservative force. Okay, I repeat. The change in potential energy is defined as the negative of the work done by a conservative force. If I had to write it down, I'd say du, U, which represents potential energy, equals minus W. W is the work done by the conservative force. Now, how will you find, let's say you are given a formula or you're given an expression for potential energy and you have to find the force. How will you do it? Well, the force is equal to minus du by dx. Right? If you have an expression for u, you have to differentiate it with respect to x, right? And that will give you f of x, or the force in the x direction. Now, this is a common tool that we use very often in a lot of problems. What else? Of course, after this, there is the basic law, which is the conservation of energy, which basically states that in a system, the energy is conserved. There is no energy can neither be created nor destroyed, and also that the net energy, that is the initial energy, should be equal to the net final energy. There is also another statement that is pretty common, which says that the mechanical energy, or the net change in mechanical energy of a system, is equal to the work done by the external forces plus the work done by the internal non-conservative forces. Okay, now this is a common expression. Let me first explain this statement. Now, what do you mean by mechanical energy? Mechanical energy is basically the sum of potential and kinetic. Okay, just the sum of that is called mechanical energy. And this statement says that the change in this mechanical energy is equal to, as I said, the work done by the external forces and the work done by the internal non-conservative forces. But the truth is, this statement is just rewriting the law of conservation of energy. If you take the conservation of energy and you apply it, you basically get this as an inference. So it's not required to think of this as another formula or another concept. It's basically the same concept that's rewritten in this format. Even the work energy theorem, as I said before, is actually the same conservation of energy that's written in this way. Cool. So now let's go to the problems. Okay, cool. Let's check this problem. What do we have here? We have this weirdly shaped curved slope, and there's this object block that's being pulled up with a force that's always tangential to the surface. That's good. What else? And it's also being pulled up in such a way that the object is slow. That is, you can see here that the mass m was slowly hauled up, which means we can assume that it's not accelerating, right? And of course, what are the details? The details given to us, this force is F, the mass is given to be m, this length is given to be L, the horizontal distance is given to be L, and this height is given to be H. Okay. And of course, they've also given us the coefficient of friction, which is nu. Okay. So what we have to find is the work performed by this force F, this tangential force F through this distance, through the whole distance. Now, how do we go about this? Well, the first thing we can see here is that this is not a constant force, right? The direction is changing, and to some extent, intuitively, we'll also know that the magnitude should change, because at every single point, the angle with the horizontal is going to change, and if it should move with the constant, if it should continuously move with zero acceleration, then the magnitude should also change, which means that every instant both the magnitude and the direction of the force is changing. So it's a variable force, obviously, and we have to find the work done across, which means that what we generally do in these cases is you break it down. You take one small displacement element, ds, and figure out what's happening there, and then basically integrate, right? You calculate the work done for that small element, and then you integrate. So in this case, how will you find that small element? So let me basically zoom in one of those areas. So this small line segment is one small line segment from that slope, let's assume, okay? And let's say it has some horizontal distance and some height, okay? And of course, the block is somewhere over here. Over there. Of course, the block will be much bigger than this. I'm not drawing it to scale. Now, let's assume that this length over here, this length is ds. Okay, it's that infinitesimal element of distance, ds, right? And we'll also assume that this angle is theta. Okay, cool. Now, what do? Let's draw the forces acting on, all the forces acting on it. First is obviously going to be gravity. So, in this direction, let's call it mg. In this direction, we have the force itself that's pulling it, that's F. So, for uniformity, I'm going to use the same color. So, F in this direction. And what else? There's also frictional force, because it's not a smooth surface. That will have a magnitude of what? Because this object is moving, it's going to be kinetic friction, right? And we know that the magnitude of kinetic friction will be mu n, where n is the magnitude of normal force, which means that there'll also be a normal force in this direction. Okay. Why will it be mu n again? As I said, it's moving. It's not static. It's not static friction. It's dynamic friction. And we know that dynamic friction will be equal to the magnitude of maximum static friction possible. So it has to have a magnitude of mu n. Okay. Now this is our this is our free body diagram for this infinitesimally small distance. Now, what we do is we'll have to find the work done in this small case. Let's call it dw. But how will you find the work done? We need to find the let's say dw is the work done, right? And you have to find this. How will you find that? Well, that will be equal to f dot ds, right? Dot product of the f vector and the ds vector. right? Because f is a vector here, ds is also a vector, you find the dot product. Now, how will you do that? What is the value of f? Well, the good thing is we can find the value of f because we know that this object is being pulled in such a way that it's moving slowly. In other words, we can say that the net acceleration is 0. The net acceleration is 0, then the net force has to be 0. So if you resolve these vectors, then you can find the value of f using the free body diagram, right? So basically then if I resolve mg vector, let me remove this, let me quickly resolve it. There'll be one in this direction, and I think that will be mg cos theta, correct? And there'll be one in this direction, and that will be mg sin theta. Let me just check if that's correct. Yeah, so this will be mg cos theta and mg sin theta. Notice that the moment I resolve those vectors, I removed the mg vector, right? Because we have already divided the mg vector into its two components. Now, some people make the common mistake of resolving the vectors, adding the components, and keeping the original vector itself. That makes it confusing. Now, you might think that there's mg, then there is mg cos theta and mg sin theta as well. No. So, it's always important to remove the original vector once you resolve the vector. So, these are all the forces. So, from this free body diagram, we can see here that F is equal to nu n plus mg sin theta, right? Because the magnitude of the forces has to be equal because there is no net force, right? Okay, but that's not going to help us. We have to find the value of n. But thankfully, in the perpendicular direction as well, the forces are equal, so we can say that n is equal to mg cos theta. Right? Now these are the two equations we get. Now we have a value for n from here, so that I can substitute in the first equation. So finally we'll get f is equal to nu mg cos theta plus mg sin theta. Okay, and if I take mg common, okay, now this is the value of f, or the magnitude of f for this instant, just this instant, okay, because that instant keeps changing because theta changes every instant, right? So now let's substitute the value of f that we found in this equation to find dw. So dw is going to be equal to mg mu cos theta plus sin theta into ds. Now there's one small shortcut I'm doing over here. See, because it is of course the dot product. dw is the dot product of f and ds, but because f and ds are in the same direction, it's been told to us that f is always tangential. We know that because they're in the same direction, then the dot product will simply be the product of their magnitudes, right? This is something we know, so we can use it directly. So that's why I'm saying dw will be mg, this term, which is the magnitude of the force, and ds, which is the magnitude of the displacement vector, right? So the product of these magnitudes will be the dot product of those two vectors. All right, cool. So this is something we will not be able to do if, for example, f was not in the direction of ds. If it was some other weird direction, then you can't do this directly. Okay. So now that we get this, let me simplify this further. sin theta. So now we have mu mg ds cos theta plus mg ds sin theta. Now how do we simplify this further? Well, if you look at the previous diagram, that is this diagram. So let me draw this small triangle over here. Okay, so this distance is basically ds, right? And we know that this angle is theta. Now, ds cos theta is going to be the base of this triangle, or this distance, right? And similarly, ds sin theta is going to be the height of this triangle, so this distance. We can also say that the base of this distance is basically dl, and the height of this triangle is dh, correct? That is, if I sum up all these small dl's, I'll finally get L. And similarly, if I sum up all the small dh's, I'll finally get H, correct? So I can directly write that ds cos theta is equal to dl, and ds sin theta is equal to dh. Now these two values I'm going to replace over here, right? And this is where the problem becomes easy. So you can say that the crux of the problem is basically at this point, figuring out that ds cos theta equals these values. So over here, if I write ds cos theta becomes dl plus mg ds sin theta becomes dh. Correct? Now when we integrate, now because this is equal to dw, now to find the net work done, we integrate both sides. So we get here, this will be capital W, let's say, that is the net work done. Now this will be equal to mu mg is constant, which will come out, integral dl plus mg integral dh. Now this obviously, integral dl is going to be the overall length, bottom length L, right? So we get mu mg into L plus right? Or in other words, I can just simplify this and write this as this is your final answer. You get the net work done is equal to mg into nu L plus h. So in this problem, we have a small body of mass. It's given to us 0.1 kilograms. Moves in a reference frame rotating about a stationary axis with a constant angular velocity. Angular velocity is given to us omega 5 radians per second. So the question asks us to find the work done by the centrifugal force when this body moves through an arbitrary path from R1 to R2. R1 is given to be 31 centimeters and R2 is given to be 50 centimeters. Well, okay, so how do you do that? Now, again, at first, when you read this for the first time, it might feel a little complicated. But one way to simplify things will be just to draw let's say you're in that frame, in that rotating frame. Okay, let's say this is that frame. This is X and this is Y. And this frame is basically rotating. Now, if you're in this frame, it doesn't really matter, right? All that matters is the pseudo forces that are in this frame. You don't have to worry about how this frame is moving exactly, correct? So let's say this is that center, somewhere over here. This is the frame that, you know, this is the point about which this frame is rotating, and the 2 points are R1 at a distance of R1 and R2. So let me draw some 2 random points. There's one over here, let's say at a distance of R1, and I have another point over here, let's say somewhere here at a distance of R2. And let's again assume that this body is moving through a random path like this. Some random path is moving like this, okay, because it says it's an arbitrary path. Now, how will you find the work done by the centrifugal force? Well, one thing we know is that this body, the centrifugal force will always be in the radial direction, correct? It will always be in a line along the line joining the point about which it's rotating to that point, right? That is something we know. So we can actually use that to our advantage. So what I mean is let's zoom into this. So let's say we are taking one small portion over here, okay, and let's zoom into that. So let's say that in that small position, the body is moving like this, okay, and the radial vector, let's say, is somewhat like this, okay, and that angle, let's call it theta. That instantaneous angle that the displacement vector makes with the line joining the point of rotation and this point, basically the line from the point of rotation, let's call it the radial vector, that let's say is theta, like this, okay? So if this vector is ds, right, then, and let's say the magnitude of the centrifugal force, let's say, is F, or the centrifugal force vector, let's call it F vector, then dW will be F vector dot ds vector, correct? And ds, and we know that the F vector will be in this direction, correct? Because it will be always radial, which means that theta will be the angle between the F vector and the ds vector. So the dot product will be F ds cos theta, correct? Okay, nothing wrong here, cool. Now what is the magnitude of the centrifugal force? Now that we know will be equal to m omega squared r, where r is the radius or the distance from the center at that point, okay? And this distance again will be ds, and this will be cos theta. So again here, dw we get is equal to m omega squared r into ds cos theta. Now how will we move forward? Well, let me do one thing. Let me zoom into this part again and I'll draw this diagram. Let's say this is same x and y, and I'm just drawing this that zoomed in bit, okay, and this is the ds. Basically this vector is ds, it's from here to here. Now I can say that if I draw two dotted lines from here, this will be r1 and this will be R2, correct? And this distance, if I extend this like this, from here, I can say that this distance, which is nothing but ds cos theta, is also the change in the radius, right? Or in other words, this distance is dr, correct? If that displacement vector is ds, then this distance, which is you can say the component of the ds vector along the radius, that distance can be dr because the angle is too small, is very small. That's the change in radius. So I can conclude that ds cos theta for that very small triangle equals dr, right? So if I bring that in this equation, I'll get dw is equal to m omega squared r into dr. Okay. Now what do we do? Now nothing. Now, so now we know the small infinitesimal value of work, which is this. So we integrate. So integrate both sides. Integral dw. This will be capital W. Let's say that's the total work done. So over here, this will become m and omega squared are constant. M omega squared into r squared by 2. But this will vary from, the limits will be from r1 to r2. And what's that given to be? It's given to be 30 centimeters to 50 centimeters. 30 to 50 centimeters. Correct? But we can't do in centimeters because we have to convert it. So let's write it in meters. So there'll be 0.3 and it'll be 0.5. Yeah. So this, if I further simplify, m is given to be 0.1. Omega is 5 radians per second. So this will be 25 into 0.5 squared by 2 minus after applying limits. Okay. Now so this will be so I get 0.1 into 25 into 0.25 minus 0.09 by 2. If, fine, how do you want to go? Cool, let's do this. 0.1. So what's 0.25 minus 0.09? Be what? 0.16, right? 0.16 by 2. I'll loop for this and for this. I'll cut this into, this will become 0.08. Okay. Finally, if I multiply all this, what do I get? I'll get 25 into 0.08 into 0.1. So finally, I'll get 0.2. So this is the final total work done. So in this question, what do we have? Well, it says that we have a ball of mass m that's suspended by a thread of length L. So let's draw that. There's a thread of length L and there is a ball at the bottom of mass m. Okay. Now, with what minimum velocity has the point of suspension to be shifted in the horizontal direction for the ball to move along the circle about that point? Now, this is slightly interesting because most of the time, most of these problems, we are used to giving the ball an initial velocity in some direction. So generally we say, give the ball an initial velocity of u or something like that, right? In this direction or in this direction. But here, this question says this point, the point of suspension here, this point is given a speed or a velocity in some direction. Let's say it's in this direction and let's call it u. So the question says, what is the minimum speed that this u should have so that the ball completes a circle about this point, about the point of suspension. Now, the moment you look at it, you might think this is, confusing. Like how will this affect the ball, so on and so forth. But the trick here is to look at this problem from this point of reference, from the point of reference of the point of suspension. Basically what I'm saying is, let's say I have a lift or a frame that's moving along with this. So let's say someone pulls it, and I have a frame like this that's moving along with that point of suspension. Now, in that frame, if you had a camera or if you're sitting in that frame, what would you see? If you look at it from that point of view, it becomes a lot easier, because in that frame, because of relative velocity, it's as good as having, if that frame was moving in this direction, then it's as good as giving an initial speed of view to this small body, right, to this ball. So basically what I'm saying is, let's say in one case I move the point of suspension with you, and in the second case I give an initial speed of view to the bottom ball. In both these cases, in that frame, right, in the frame of reference with respect to the point of suspension, the way the ball moves will be exactly the same, right? So therefore, now we move to this frame. Now therefore, in this frame, thanks to relative speed or relative velocity, this body has an initial speed of view in this direction. Now what do we do? Now it's pretty simple. Now you have to calculate the minimum speed u required for this ball to complete a circle in this frame. How will you do that? Simple. So let's assume that so many people over here also, they generally just apply a formula and say that this should be the minimum speed, but that's not technically right. Think about what is required for this ball in this frame to complete a full circle. So the ball in this frame is moving like this. It's coming to the topmost point. Now, what is the minimum speed? So that, what should happen at the topmost point so that it completes a full circle? The tension in the string at the topmost point should be non-zero, right? If it is zero, or if the tension, basically, let's say the ball goes like this, and somewhere the tension becomes zero, less than zero, it'll just fall like that, right? Similarly, like this. At a point, only if the tension is still non-zero when it reaches the topmost point, only then will it continue to move like this, and therefore will complete a circle, right? So the minimum condition for this ball to complete a circle is that the tension is non-zero when it reaches the topmost point, right? So let's analyze that topmost point. Let's go to that. Let's draw the free body diagram in that topmost point. Again, I'm solving this problem in that frame of reference, right? So this is your point of suspension. This is your spring, and the ball is over here. It's come like that over here on top. Okay. Now, at this point, let's say if I draw the free body diagram, I'm going to draw it separately over here to make things easy. There is one tension force in this direction, correct? There is an mg pulling it downward in this direction, and what else? That's it, right? Right. So these are the forces T and mg in over here, and also this ball in this frame will be moving with some speed at this point. Let's call this. Let's call that v. Right? Then we can say that T plus mg will be equal to mb squared by r, right? Because that will be the centripetal force. T plus mg will be radial in direction, so that will be equal to the centripetal force over here. And since it's moving with some velocity v, some speed v at this point, T plus mg should be equal to mv squared by r. R in this case, of course, is the length of the string, so it will be L. Right, mv squared by L. Okay, now what we do? Well, let's make this simple. So I'm going to say T is equal to mv squared by L minus mg. Okay, now what was the condition I mentioned? I mentioned that for it to complete a full circle, T should be greater than 0 at this point. So let's apply that condition. So T greater than 0 which means that mv squared by L should, minus mg should be greater than 0, or mv squared by L should be greater than mg. This implies that v squared by L should be greater than g, or v should be greater than root Lg. Right? So v should be greater than root Lg, which means that the minimum speed that we should have, v min, should be equal to root Lg. So at that point, if it had any speed less than root Lg, it will not complete a circle. So the minimum speed it should have, so that it completes a circle, is root Lg. So what we need to find is the minimum value of u so that this ball reaches a speed of root Lg at the topmost point. Correct? I repeat, the minimum initial speed so that the ball reaches a speed of root Lg at the topmost point. How will we do that? Simple, we can use work energy theorem, because in these cases it's very simple to use work energy theorem, right? So what is the total change in that frame of reference? One thing I forgot to mention is that this is an inertial frame of reference, because in this frame of reference it's moving with a constant speed v, not with an acceleration. So it's not a non-inertial frame of reference. It's still an inertial frame of reference. Okay. So in this frame of reference, what if we apply work energy theorem? What is the delta K? What is the change in kinetic energy? That will be half m being the mass. Let me change this. Delta Ke is equal to the final kinetic energy minus the initial kinetic energy. So what's the final kinetic energy? Half m into v squared minus half m into u squared this should be equal to the work done by all conservative and non-conservative forces. Here there are no non-conservative forces. The only forces here is gravity, right? Of course there's tension as well, but tension is always going to be perpendicular to the displacement in that frame, right? So there is no work done by tension in this case. There's only work done by gravity. So what is the work done by gravity? Gravity is pulling downward. It's moving a distance of 2L. So work done by gravity is minus mg into 2L. Correct? Because that's the displacement. Yeah. So one thing that one common mistake that is generally made at this point is that people tend to forget this work done by the pseudo forces, because that also needs to be added in that non-inertial frame of reference. Change in kinetic energy is equal to the sum of all the work done by all the forces, including the pseudo forces. In this case, it just happens, as I said, this is not a non-inertial frame. This is still an inertial frame, so there is no work done by pseudo force. So these only the work done by gravity is the work done over here. So if I simplify this, I get half into v squared minus u squared. First I'm cutting m, is equal to minus 2gl, right? Now we can substitute the value of v that we know, because we need to find the minimum value of u. We'll directly substitute this value of root Lg, v equal to root Lg. You can substitute that over here. So I get half into Lg minus u squared equals minus 2gl. Okay, let me just expand this to make things clear. 2 minus u squared by 2 minus 2gl. LG by 2 plus 2GL equals U squared by 2. Let me take LG of 1 by 2 plus 2 equals U squared by 2. This means that 5 by 2 LG equals U squared by 2. This gets cancelled, and then U is equal to root of 5 LG. So the initial speed that the ball requires is root 5 LG. I know this is something that we use as a formula in this video. It's better to go through this process because it helps you understand. Okay, so U is equal to root 5 G, and this also means that the initial speed, that the point of intersection. So what the question asks is not the speed of the ball, because the ball is not getting any speed. What the question asks is what should be this speed, the speed of the point of suspension, and that will basically be the same, right, in magnitude. So the answer will still be root of 5 LG.
For more videos and live lectures on the JEE, click on the subscribe button now.